Okay, let's get started for our Friday class. So remember last time we were discussing integrals, right? Or expectations in the probabilistic setting. So the idea was to build the integral, construct the integral, starting from basic random variables, starting with the integrals of basic random variables. So we followed some steps. First some, then the next some limits, etc. So if we have a probability space or a measure space in general, and a numerical random variable on it, so if you have a measurable function, we follow the So the first step was to define the integral of an indicator function where A is a measurable set. Okay? So this was the easiest step because in this case we define the integral of x as mu of A. So this is a constant function. This is a function that takes the constant value 1 on the set A and 0 everywhere else. Therefore, we define the area in some sense under this function with respect to this measure mu as the measure of the set A. So the step 2 was to extend it to simple positive functions. In which case the integral was defined in a way to ensure linearity, right? Meaning that this is the sum of AIs, mu AIs. And in step 3, we extended this definition to arbitrary positive measurable functions using the canonical way of approximating them. So remember, this Fn was a standard approximating function. So it takes the value I minus 1 over 2 to n on this interval I minus 1, 2 to n, to I, to 2 to n. So it's a lower approximation of the function, and it forgets what is happening after the value n. So this was defined for all x between 0 and plus infinity. And if you apply this deterministic function to x, you get something that is a simple positive function and that is below x. And we had z1, z2, etc., with limit being x. Therefore, by the monotonicity of the integral, at that step, we also had the integrals of those simple functions increasing, and they have a limit. And we set this to x d mu. This was the way we defined the integral for positive measurable functions. So we proved monotonicity and linearity of integral in all of those steps. And in addition, in step 3, we had the monotone convergence theorem, which tells us that if you have an arbitrary sequence of positive measurable functions that are increasing to a limit, okay, then the integral of the limit is equal to the limit of the integrals of the functions in the sequence. Okay? In particular, you can pick, you can fix some x, okay, that is positive measurable, and take any sequence of functions that are measurable, but they should be increasing to that function x. Okay? So you can replace those Zn's, the standard sequence, with an arbitrary sequence of increasing functions, I mean functions that are increasing to x, okay? And then by monotone convergence theorem, this sequence doesn't matter. You will always get, as the limit of the integrals, you will always get the integral of x. So by mon, if you have an arbitrary sequence increasing to x, then the limit of those integrals will give you the integral of x. So the sequence, the choice of the sequence does not really matter. So you don't have to use the standard sequence of approximating functions. So our first job today is to extend this definition to functions which can take plus and minus values, right? Positive and negative values. So let's say this is our step 4. So suppose x is just numerical and measurable. So in other words, suppose nothing else but this, okay? So in this case, we can write x as x plus minus x minus. Remember that x plus is the positive part of x, and x minus is the negative part of x. And they are both positive measurable functions. Positive measurable. Therefore, their integrals are always well-defined, in 0 to plus infinity by step 3. So the way we're going to define the integral of x is as follows. Just set this to the integral of x plus minus integral of x minus. When? When can we do this? You have a number between 0 and plus infinity, and another number between 0 and plus infinity. Do you have any problems with those two numbers when you take their difference?
Right function be plus infinity. Otherwise we have minus infinity.
So if this is plus infinity and this is plus infinity, you have an issue. Otherwise, you never have an issue, right? So if this is not infinity or this is not infinity. Okay? So otherwise, so if they are both infinity, we say the integral, so x d mu, does not exist. And if they are both finite, we say we have x d mu, a real number, and we say that x is integrable or mu integrable. Okay? So the integral exists if not both of them are plus infinity, and if both of them are finite, the integral is even a real number, and you say that it is an integrable function, okay? Integrable random variable. And in fact, we have a notation in the real valued case. So if you look at all x omega to r, okay, so x is measurable. I mean, x is just mu integrable, let me say, which automatically needs measurability. Okay, so the collection of all such random variables is denoted by L1, okay? L1 of mu. You can also put omega f mu, or just mu. So this is the space of real valued integrable functions, okay, with respect to a fixed measure. So do we have to discuss something like the compatibility of step 4 with step 3? Well, let's discuss it. So does step 4 really extend step 3? Meaning that if we take a positive function and apply step 4, do we have any different results than the ones that we got in step 3? Well, the answer should be no. If x is positive, this means x minus is just 0, right? This disappears. So x minus is 0 means the integral of x minus is just 0. Therefore, by step 4, by this step, the integral of x is just defined as x plus d mu. And the integral of x plus is defined by step 3. So you get the same definition. Okay? So remark is that step 4 extends step 3. In other words, if x is positive, then x plus is x and x minus is 0. So we don't have any issues. So what is next in our program, in our agenda? So what properties do we need to check? What did we check in step 2? What did we check in step 3? Do you remember? 2 very important properties, right? Integral is always what? Monotone. What else? Linear, right? So we have to check monotonicity and linearity. Okay? Let's check. So maybe first monotonicity. So let's say we have xy that are positive, that are just measurable and numerical. Okay. So we have x less than y implies integral of x is less than integral of y, provided that we have no issues. So I will list two cases. So we have this in each of the following conditions. Of course, if they are positive, it is automatically satisfied, right? So I don't want to list that one. So the new ones are this. So x d mu and y d mu exists. Okay? Or you need to have either this is integrable or this is integrable. So the only thing that we would like to avoid is the case where these don't make sense. Okay? So we just want those integrals be well defined. Okay? So let's check it. Okay? So we have x less than y. Okay? So you have a function x and another function y. So x always takes values that are below the values of y. So this implies what? So what can you say about the positive and negative parts? So if you look at the positive part of x, so if x is positive, if x takes a positive value, right, then this will also have a greater value. The positive part of y will also have a greater value than the positive part of x, right? And how about x minus and y minus? This is the opposite relationship, right? Because when you have a negative value for those, to get their negative parts, you switch their signs, right? So these are always positive, whereas when they take negative values, they have this order. Therefore, when you switch the signs, you should have the opposite order. So y minus is less than x minus. And in fact, this is if and only if, because you can just write it as minus x is less than minus y. Minus x minus is less than minus y minus. And add the two equations to get x is less than y. Right? So this is if and only if. So now, why did we do that? Because we did it because these are positive functions. So now we have monotonicity for positive functions. By monotonicity in step 3, we have the integral of x plus is less than the integral of y plus. And minus integral of x minus is less than minus integral of y minus. So all we need to do is to add those two equations and get x d mu is less than y d mu. Just make sure there is no infinity minus infinity. And you don't have infinity minus infinity in those cases A and B. So if you look at A, okay, x d mu and y d mu exist. So if x d mu exists, this means what? This and this cannot be plus infinity at the same time. Okay? One of them is finite. Therefore, you never have an issue infinity minus infinity. Same with y. So if the integral of y exists, this means this is well defined. So you always have one of them being finite, so you can add them. So in A, we don't have an issue. Everything's fine. Right? And in B, let's say we have x is integrable. So what does that mean? Well, the integral of x plus and integral of x minus are both finite, right? This is a finite value, and this is a finite value. So if this is a finite value, this can still be plus infinity. But if this is a finite value, so if this is integrable, right? If the integral of this is finite, then the integral of this must be finite as well, right? So integral of x minus is finite, then integral of y minus is finite. Therefore, you don't have you have this term being finite, so you avoid infinity minus infinity. Okay? So in this case, y minus is also integrable. And symmetrically, if y is integrable, then x minus, or probably x plus, let's check. Y d mu is finite, so this has a finite integral, therefore x plus is integrable. So in both cases, you avoid infinity minus infinity. And the other one is linearity. Okay. So let's say x and y are integrable. and AB in R, then we have linearity. Then the integral of ax plus by is a integral of x, b integral of y. Okay. And we will proceed in 2 steps. The first step is where you have just the difference of x and y. Okay, let's show this. So this is the case where a is 1 and b is minus 1. Of course, if x is bigger than y, then this follows directly from linearity in step 3, since you can write x as y plus x minus y, right? And then you have x d mu is y d mu plus x minus y d mu, right? And they're all finite. Therefore, this is equal to this minus this. So what happens in general? In general, if we don't have x bigger than y, we can look at the region where x is bigger than y and where x is less than y. So we can write x minus y as x minus y under this condition and x minus y under the other condition. Okay. So then we have what? So we're looking at the integral of x minus y d mu, right? So it can be positive or negative. Therefore, we first need to apply the definition of integral. So x minus y positive part and x minus y minus d mu. Sure.
How did you conclude that if we have x is equal to y plus x minus s, this line after that? Because we only know x minus y is positive for now, and we don't know any equality of the integrals yet.
Ah, okay. Okay. Maybe I should have said these are also positive. Thank you. Thank you. Okay. Great. So now all are positive. Okay. So we applied the definition of integral because x minus y is a signed function. It can take positive or negative values. So this is the region where it is positive. So we look at the positive part of it. So when do we have non-zero values? Of course, when x is greater than y, right? So this we can write as x minus y, indicator x greater than y, d mu. And here we have non-zero values, and those non-zero values will be equal to y minus x when x is less than y. Right? So if this is 0, this means what? x is less equal y. Sorry, this gives you a non-zero value when x is strictly greater than y, or let's say x is greater than y, okay? So in this case, the value is equal to just x minus y. If x is strictly below y, this indicator will give you 0. And in that case, you will have a negative value in the positive part function, which will also give you 0. Maybe here we should assume when x, y are positive. I should also add it here. Okay. So we assume x and y are all positive. Okay. Okay. So now what? Now what? So these are, this is x indicator x greater than y, minus y indicator x greater than y, d mu. And this is y indicator x less than y, minus x indicator x less than y, d mu. And this function is greater than this. And this function is greater than this. And they are all positive functions. Therefore, we have linearity everywhere. Y, etc., etc. So let me write the other two terms. Y indicator x less than y, and x indicator x less than y, d mu. Right? And then you can bring the two together, etc., etc., and check that. I will leave this to you, that this gives you what? X d mu minus y d mu. And step 2 is where you have the general case, okay? General case. And I will also just give it as a sketch. So here's the idea. So you want to use step 1, where you have positive functions only, okay? So in that case, you can do the following. So you can write a as a plus minus a minus, x as x plus minus x minus, and then b as b plus minus b minus, and y plus minus y minus. And this is going to give you a huge expression for ax plus by. Right? I guess 8 terms. There is going to be 8 terms. And then use step 1 to finish, to prove linearity. You're going to get 8 integrals, so I don't want to write them down one by one. But the idea is to reduce everything to the positive case by looking at the positive and negative parts of a, x, b, and y. You just need to deal with this minus sign. That's why we needed step 1. Okay? So 4 of those terms will have a positive, a plus 1 in front, and the other 4 will have minus 1 in front. Therefore, you need to deal with this negative sign, but nothing else. The rest is just linearity for the positive case. Okay, so now we're kind of done with the construction of integral, at least for real valued functions. So what we would like to do is to add a few more limit theorems. So remember, the most important limit theorem is what? The monotone convergence theorem, okay? But last time we also proved Fatou's lemma and also a different version of monotone convergence theorem, which doesn't require the functions being increasing, but instead you look at a series of them, right? Integral of the sum of xi's. So today we're going to add a few more limit results. Which will not require positivity. First, let me recall Fatou's lemma. So if x1, x2, etc. are positive measurable, then the integral of the lim of xn's is less than the integral lim of the integrals. Right? And as an exercise, what you can do is to relax it, okay? Relax the part where you need positivity. So now we define integral for not necessarily positive functions. So we can call it some kind of a relaxed Fatou. Okay? So if x1, x2, etc. are above some y for some y integrable, then you still have the same result. Okay? And the idea of the proof is very simple. Well, you want to prove the relaxed Fatou's lemma using the usual Fatou's lemma. What you can do, you need to define positive measurable functions. And these are not positive, but greater than y. Therefore, you can just look at x1 minus y, which is positive, x2 minus y, which is positive, and apply Fatou's lemma to those, right? So the idea is very simple. But the main reason to give this exercise is actually to motivate the reverse Fatou's lemma. So here's what we're going to add. So now it's the new limit theorem. So reverse Fatou's lemma. So reverse meaning that it's going to be about lim sup. And it is completely symmetric. So if x1, x2 are measurable numerical and we have xn less than y, let me write it this way, and there is y that is integrable such that xn is less than y for all n, then we have what? We have the integral of lim sup is not below but above the lim sup of integrals. So it is just the reverse, but how should we prove it? Or maybe the relaxed Fatou. You can even use relaxed Fatou, I guess. Yeah, let's use relaxed, right? It is just the sign switched, right? Just multiply by -1. So we have minus xn above minus y for all n. So therefore, we are in the setting of relaxed Fatou. Relaxed Fatou. note that minus y is also integrable. Right? If y has finite integral, minus y also has finite integral, and it is just the negative of the integral of y. So by relaxed Fatou, we have lim, let me write it this way, lim inf of minus xns is less than lim inf of minus xns. Right? So what is the lim inf of minus of a sequence? It is, okay, who wants to guess? Lim sup of the exact one. Almost. Minus of the lim sup, right? So this is equal to the minus of the lim sup. Okay? And this you can just write as minus xn d mu. And now this is again a lim inf of minuses. Therefore, it is the negative of lim sup of xns. And this is equal to negative integral of lim sup. So just flip the signs, you get what you need. Okay, another big convergence result, dominated convergence theorem. Okay, so again, let x1, x2 be numerical measurable functions. Assume there is y, which is integrable, such that xn is less than y in absolute value. In absolute value for all n. And furthermore, assume also that, let me just write it this way, the limit of xn's exists. Okay? Exists. Okay? Then this limit is integrable, and its integral is given by the integral, the limit of the integrals. So that's an important result because, first of all, it is talking about exact limits, not lim inf and lim sup. So you can apply it in the case where the sequence converges, but you don't need monotonicity, okay? But instead you need a condition which stands for which this word dominated stands for, okay? Dominated. So there is a y which dominates the sequence in absolute value. Okay. Okay. Now, how are we going to do that? Well, let's write down what we have, right? So we have minus y less than xn less than y for all n. Okay. So what does it look like? Well, the first part looks like this. Xn is above something. And the second part looks like this, where xn is below something, below an integrable function. So we're going to apply both, right? So this is for relaxed Fatu, and this is for reverse Fatu. Okay, so let's write down what this is, and hopefully we will be able to show that it is equal to the limit of the integrals. So let's write down the integral of the limit. Integral of the limit. What is the limit? Limit means it is equal to lim_inf and also the lim_sup, right? So we say the limit exists, therefore it is equal to lim_inf, and it is also equal to lim_sup. So let's use lim_inf first. Lim_inf xn d mu. Okay? So that we are in the setting of relaxed Fatu. Okay? So integral of lim_inf is less than lim_inf of integrals. Now we need to use reverse Fatu, which has lim_sup of integrals is less than integral of lim_sup. But we have lim_inf of integrals. What's the relationship between the lim_inf and lim_sup of integrals? Lim_inf is less than lim_sup, right? We know it. Lim_inf is less than lim_sup. Okay, maybe I should have used those colors properly. So this is where we used relaxed Fatu, and now we use reverse Fatu. Okay, which is integral of, which says this is less than the integral of lim_sup. And what is lim_sup of xn's? It is the limit of xn's. Therefore, they are all equal. All are equal. In particular, we have the equality of the lim_inf and lim_sup of integrals, which means limit of integrals exists. Exists, and it is equal to this one, the integral of the limit. We should also say that this is a finite number, because if you look at the statement of the theorem, this says this limit is integrable. So let's argue that this limit is, has finite integral. Well, this is still coming from here, right? So by sandwich theorem, right, the limit is also between minus and plus y. So the integral of the limit is between plus and minus integrals of minus y. Therefore, it is a finite number because y is integrable. Okay, so I think that is it about convergence results. So what do we have? We have three very important convergence results, okay? The first one is the most important one, and it is the monotone convergence theorem. We spent so much time to prove it last time on Tuesday, right? So today we kind of used its consequences. So one consequence was Fatu's lemma, and that's the second important convergence result. The main point of this result is that it doesn't require the existence of limits. So you can use it for an arbitrary sequence of measurable functions, as long as they are positive or as long as they have a lower bound which is integrable. And there is the reverse of it, dealing with the lim sup. Okay? So these are of equal importance. So if you know one, you can easily derive the others. So these are like Fatou type convergence results. And finally, there is dominated convergence theorem, which requires the existence of limit. Okay? We assume that the limit exists. Okay? And then if the family is dominated by an integrable function, okay, in absolute values, meaning that it is both, so xn is lower and upper bounded by an integrable function. And in that case, we have the same conclusion as with the monotone convergence theorem, meaning that the integral of the limit is equal to the limit of the integral. Okay? Just for completeness, I'd like to add a step 5 for complex valued measurable functions. So if x is real part of x, I times imaginary part of x is a complex valued measurable function, then we define the integral of x d mu as a complex number, which is the real part of x integrated plus I, the imaginary part of x integrated, provided that both the real and imaginary parts are integrable. So when I write L1, it is always L1 mu, okay? Since mu is fixed in our setting, I don't write it too much. So since to be able to talk about complex numbers, you need a real valued real part and an imaginary part. So you want to avoid infinities here and here. You make sure these are just real valued and integrable functions. And that's it. That's it. So the only use in this course of such construction will be for Fourier transforms. We'll use it for Fourier transforms later, probably in 2 weeks. Okay, otherwise, we're done with the construction of integral. And in the next hour, we will discuss some examples and also some further properties of integrals. Okay? So let's give a break.